let's talk about polar. So we've talked a little bit already before the video about the meaning of polar coordinates. Let's just go ahead and like notate it down so that we have it written down. So I am notating polar coordinates this way. So 3 angle 90 degrees means that we're going to face in a direction of 90 degrees and move a distance of 3. And in general, rather than like x comma y, we'll write r angle theta. So r is a distance and theta is a direction. And the direction is always measured relative to the 0 angle, like the horizontal 0 angle. So go ahead, let's make an xy plane. And let's just like plot a couple of these to make sure we feel good about them. We're going to have to estimate the distances a little bit. So 3 angle 90. Actually, here, I'm going to pause the video. Why don't you just like real quick with your neighbors guess where all 5 are? And then we'll confirm. That'll be more fun. So let's double check. In angle of 90 degrees, we're always measuring from pointed straight to the right. So 90 degrees is straight up. We go a distance of 3. So up here is point A. Here, if we're at an angle of 45 degrees, that's sort of along this dotted line, a distance of 3, I wouldn't put it out here because that's too far. That's, if you think about Pythagorean theorem, that would be 3 over and 3 up. So the distance this way would be square root of 18. But 3 is going to be maybe, I don't know, kind of here-ish. And the exact distance isn't important. Just realize we have gone 3 in that direction. All right, so these next 3 are a pair because I want to be really clear about what does negative angle mean and what does negative distance mean. So 2 at an angle of 30. Angle of 30 is kind of this way-ish. Distance of 2 is approximately right here. So we'll call that C. If I go a distance of 2 with an angle of negative 30, remember positive angles wrap that direction, anti-clockwise. Negative angles wrap the other direction, or clockwise. So this is an angle, here let's write 30 degrees, and this will be negative 30 degrees. And so again, I'm headed a distance of 2 in that direction. All right, so now we're back to an angle of positive 30. What does it mean to go a distance of negative 2? Well, let's imagine, right, the other direction is a good guess. So look at the direction the arrow is pointing. So that would be like a positive direction if your angle was 30 degrees. So instead of going 2 in that direction, if I go negative 2, that would be in the opposite direction along that same line. So approximately here. So that's the key bit to know, and you can feel free to like annotate this if that would be helpful. You could say negative distance goes in the other direction. That fact is going to lead to some like interesting graphs later on. So kind of file that away. That sometimes your angle might be pointed in one direction, but your points might lie in the opposite direction. Yes, the video is restarted. So the question was, hey, does that mean that you could have 2 different polar coordinates that point to the same spot? Let's, yeah, so this one that's like 30 degrees negative 2, if I go all the way around to 180 degrees and then have 30 more, so that's what, 210? Yeah, thanks. So that's 210. I could go positive 2 in the direction of 210, and that also points me at E. Yeah, and both of those coordinates describe that same point. Excellent point. All right, restarted. So these weren't in the notes before, but as the other pre-calc teacher pointed out, this is arguably an important thing to need to do. So step 1 is become vertical, and then step 2 is going to be copy this down. If we want to convert from rectangular to polar, let's sketch a kind of generic picture here. So if I'm describing this point with rectangular coordinates, it's like some distance over and some distance up. So this would be the x coordinate, this would be the y coordinate. But I can describe that same point as some angle, theta, and some distance, r. So now we can just use like trigonometry we know to switch back and forth between them. So if I was going to use, let's use SOHCAHTOA. So sine theta is opposite over hypotenuse. So sine theta is y over r. I guess let's write it out. So sine theta is y divided by r. So if I want to know what's y, let's just multiply by r on both sides. And now I've got y is r times sine theta. Similarly, cosine theta, SOHCAHTOA says adjacent over hypotenuse. Adjacent is x, hypotenuse is r. So x over r, multiply by r, and that gives us that x is r cosine theta. Yeah, so like back when my programmers didn't use polar coordinates to program Hexagon, or whatever that Hexagon game was, if they had, this is what they would have used to figure out the XY coordinates on the screen based on their polar representation for the location of the dude, the ship. Cool. So you like plug in the R, you know, plug in the theta, you know, you can find X and Y. All right. As long as we're doing this, let's do the other direction. So this was find X and Y if you know R and theta. Let's do how to find R and theta if you know X and Y. So let's see. R. So what's your favorite equation that starts with a P that will let us find the distance of R? Oh, it is. It is the Pythagorean theorem. So x squared plus y squared, square root, is R. So R is root x squared plus y squared. Okay, what about theta? It's like we got all these, trigonometric relationships. So we know already sine theta is y over r, cosine theta is x over r. There's a key one that we're not using yet. Yeah, so we're saying, let's think about that last one, tangent theta. Tangent theta is opposite over adjacent. So tangent theta is y over x. But we don't want to know tangent of theta, we want to know theta. So how do you undo tangent? It's with tangent inverse, also sometimes called arctangent. So arctan of y over x is how you can calculate your theta. Okay, cool. Eventually maybe we'll use these for something. Okay, video restarted. So the top section is just about polar coordinates. Now we're going to talk about polar equations, which are equations that use polar variables. So here's what I mean. This is a rectangular equation, y equals x. And all that, and like usually what you do for these is like, let's pretend you're in algebra 1 and you don't know what y equals x looks like. What you do is you plug in your x value to find your y value and you plot all the points, right? So if you're into writing stuff down, write this down even though it's obvious because it's going to contrast with polar. So plug in x to find y. And we could plug in like x equals 0 and 1 and 2 and 3 and so on. And then y is 0 and 1 and 2 and 3 and so on. And then we can plot all those points. Here's 0 and 1 and 2 and 3 and so on. Let's go ahead and label these points A, B, C, D. So obviously, even though we only plugged in a couple of points, there's an infinite number of x, y values that make that equation true. So like we could choose 1/2, 1/2, or 3/2, 3/2. So even though we only plotted those 4 points, we try and connect them all with the shape that we know that they're on. So unsurprisingly, this is the shape of a line. Okay, so now let's think about that same thing, but with polar. So this is a very simple polar equation, r equals theta. And let's think about what it means. Over here, you plug in an x value to find a y value, and then you plot those coordinates. Here, we're going to plug in an angle, theta, to find what distance we should move in that angle to reach the point on our curve. Okay, video back. What if x, y are not our coordinates? What if this is r and this is theta? So at an angle of 0, we go distance 0. At an angle of 1, we go distance 1. At an angle of 2, we go distance 2. why don't you like think it out for a second? What would it look like if we plotted all those polar points and then tried to connect them? Go. All right, we're back. I heard a couple of people say the S word, spiral. Yep, that spiral is the word. It's all on the video, folks. So, all right, so angle of 0 is like facing to the right. A distance of 0 is right here. So let's put the point A here. Let's pretend that the angles are measured in radians. So let's think, where's 1 radian approximately? A full circle is like 2 pi radians. Pi is like a little bit more than 3. So there's like about 6 radians in a whole circle. Okay, so if there's 6 radians in a whole circle, that means there's 3 radians in a half circle, which means 1 radian is like approximately 60 degrees, maybe a little bit more than 60 degrees. But like we're just approximating here. So this is now an angle of 1. Let's go a distance of 1, which takes us to about here. So this is point B. Point C, an angle of 2 radians, is going to be a little more than 120 degrees, so over here. A distance of 2 takes us to about here. 3 radians is a little bit, less than or more than? More than 180 degrees, so a little bit over here. Distance of 3 takes us to about here, so that's D. Okay, so it's definitely looking spirally. Maybe. Here's the number one thing that students who aren't used to thinking about polar do wrong. When it comes time to connect them, they're like, okay, A and B, I'm going to connect A to B straight like this. I'm going to pause the video. Can you tell your neighbors, like, why does that not necessarily make sense? Okay, we're back. As was pointed out to me by the students, 3 radians is a little less than 180 degrees. So let's revise D to be over there. Okay, so here's the way of thinking. You know those like old, do you guys ever watch those old like submarine movies, spy movies? Do you know what I'm getting at? So they're like old radar, like has that screen with like the rotating line that shows like boop, boop, like there's where the submarines are. So that's kind of how I think about plotting these points. It's like here we're at an angle of 0. As our angle goes up, the distance we move along that line also increases. So here I'm going to draw a bunch of intermediate steps here. So this is me imagining each one of these lines is the angle went up a little bit. So angle 0, distance 0. Angle a little bit more than 0, distance a little bit more than 0. I increase the angle a little bit, I increase the distance. I increase the angle, I increase the distance. I increase the angle, I increase the distance. So if we're going to connect them, really they end up connecting with sort of a curve like this. And a big thing that I want you to take away here is thinking about it very conceptually. When I taught calculus and all the pre-calc students got there and it came time to do polar stuff, the way they thought about every single polar equation was they plotted a bunch of points, like mindlessly plotted them and then tried to connect them, sometimes rightly, sometimes wrongly. I want to emphasize that there is like a more natural way of thinking about them. You don't have to just robotically plot points. You can think about it. Let's break out the Desmos sketch here. You can think about it using that sort of process that I described. So let's recreate this. Here's radius as a function of t for theta. So I'm going to make it go real slow now. So I'm just about to play theta increasing. So you see that as theta is increasing, the distance of my point along the line is also increasing. Maybe this was too slow. It's just very suspenseful. But that was about 1 radian there. And so you see it's connected with this kind of line. So each tick that this moves to a greater angle, the point is moving like 1 tick longer in that direction. So it's tracing out that spiral. Okay, I'm going to pause the video. And so like one thing just to notice and appreciate is simple equations in rectangular produce shapes like lines. Simple equations in polar might produce things like spirals or like circles. So different things count as basic depending on what representation you're using. So the copy didn't come out that well, but go ahead and make this be a filled in line up here at 4. Let's have that be a closed point, filled in line. And then the rest of them look okay. So deal with this in 4 quadrants. You can make little dotted lines here. Not asymptotes, I'm just trying to separate the quadrants. So this is the first quarter circle from an angle of 0 to an angle of pi over 2. So that's this part of the circle. Here we've got an angle of pi over 2 to an angle of pi here. And the height of the points here are telling us the radius. They're telling us the distance in that direction. So just as a quick sense check, if I call this point B right here, agree with your neighbors. Where would you plot B if you were plotting this point as a polar coordinate? Where is B plotted if it's a polar coordinate? Okay, quick answer. It's an angle of pi over 2. It's a distance of 1.5. And again, sorry for the bad copy. You can fill in the heights there. So an angle of pi over 2 is straight up. Distance of 1.5 takes me to about here. So that's the point B. So now go ahead and convert this rectangular graph into a polar graph by thinking really carefully about, like, what does this horizontal line turn into in the polar graph? All right, here we go. So, but for angles between 0 and pi over 2, so this interval here, the height is always the same. The height is 4. So I could think about it as, like, let's just select several points along the way here. So that would be like a couple of different points with an angle starting at 0, equally spaced going up to an angle of pi over 2. But the distance is always the same. The distance is always 4. So an angle of 0, we've got 4. And an angle of 30 degrees, we have 4. 40 degrees, we've got 4. 60 degrees, we've got 4. And then open circle here at pi over 2, 90 degrees is 4. And then if we're going to connect them, we'd connect them in a circle, because it doesn't matter what angle we chose here. Every single angle has a distance that's the same of 4. So we got this big old quarter circle out there. All right, what's happening between pi over 2 and pi? So we already have our point B here is at 1.5. And then it looks like, imagine your radar. As the radar is rotating this way, the distance is going down. So a distance here is decreasing towards the origin. It's a little hard to tell with my pen and the finger. But something like this. Because by the time that I'm pointed this way, the distance in that direction is almost 0. Okay, so that takes care of that region. Pi to 3 pi over 2 is like what happens as I continue to rotate around this way. And you'll notice that it's symmetric. So once I'm like slightly more than 180 degrees, my radius is slightly larger than 0. As I increase the angle, the radius increases until eventually, by the time I'm pointed straight down, I'm back at 1.5. So it's sort of like 2 sort of semicircles. And then for this last part, again, we have a constant height at 1, starting at 3 pi over 2, so open circle, and then this is constant height at 1. And then I didn't tell you if this was going to be open circle or closed circle. Okay. Questions? Yeah. Yeah, so you don't usually include arrows to indicate direction. It's usually you just evaluate 0 to 2 pi.